Okay, so now we've seen what the KK conditions are. Let's do a couple of examples to just sort of get our head around how they work in practice. These won't be examples where I'll find the minimizer. I'll sort of just check that the KKT conditions work. So hopefully these will give us a bit of a feeling for what's going on here. Okay, so here are some examples of how the KKT theorem works in practice. So here it is again. So remember that the first expression in the KKT conditions is the gradient of this Lagrange-like function. So to find this new function, f of x plus the sum of lambda I gi x, and then differentiate that and set it equal to 0, and where we sum over the active constraints, and then we have g of x is less than or equal to 0, and the Lagrange multipliers are positive at the minimizers. So, okay, so let's check that these that all of these conditions actually hold up on a few real examples. So here is an objective function. So an objective function that's really simple, right? So a two-dimensional parabola that's got a minimum at 0, 0. It's got a minimum at the origin. So you know that that function f of x, x1 squared plus x2 squared, is going to have a minimizer right there at the origin, right? And so the gradient of that f of x is 2x1, 2x2, pretty straightforward. And then the constraints that are going to form my convex set here are going to be being underneath the line x2 minus x1 is equal to 0, so being in that region, and being above this parabola. It's this red curve here, x1 squared over 2 minus x2. Minus 2 has got to be less than or equal to 0, so in other words, I've got to be above the parabola. So I've got to be in that region there. Where's the intersection of those two? It's this green area here. Now, of course, the minimizer here, we know the minimizer is at 0, 0 at the black dot there. So we know that x star is equal to 0. Right, so it's 0, 0. Yeah. And that means, which is, that's in the interior of this convex set, right? So if the minimizer is in the interior of the convex set, it doesn't sit on the boundaries anywhere. And it means that the minimizer, the constraints are inactive. So it means the index set here, the active set, as I should call it, that's phi, right? Neither of the constraints are active. So looking back at the KKT conditions here, this whole second term, which sums over everything in the active set, that's equal to 0. So all I have here is that the gradient of f evaluated at this minimizer, x star, that's got to be equal to 0. And of course, if you think about the gradient of this function here, and you evaluate it at 0, 0, right? So if you evaluate this function, 2x1, 2x2, at 0, 0, then yeah, of course that's equal to 0. So the KKT conditions check out there. That's sort of the straightforward example. And actually, it ends up being just an unconstrained optimization problem. All I did to solve this was just take the gradient of f of x there and set it equal to 0. I didn't actually need to bother with the constraints here, and that's what's happened with this. So that's the most straightforward one. So here's one slightly different. So I'm still minimizing the same objective function, and so we've got some level curves of that objective function here. So the global minimum is of course at the origin still of that objective function. But now I want to find the minimizer subject to these constraints that I have to be in this green region. It's my convex set, over here to the right. So of course the minimizer is going to be at this point here, so at 4, 0. And at that point, the gradient of f is going to point in the opposite direction of negative of the gradient of G2 here of the parabola. So just as we saw for Lagrange multipliers, those gradients will point in opposite directions. So let's see what the KKT conditions say here, right? So in this case, you know, I of X star, you know, what's going to be the active constraint here? Well, it's just the second. It's just the second constraint, just the parabola here, right? Like the minimizer is not sitting on the blue line, right? It's not sitting on that vertical line. It's just sitting on the parabola. So there's only one of these constraints that's activated here. Okay, so that means what are the KKT conditions going to say? They're going to say that at this minimizer, f of x star plus lambda 2 times the gradient of G2 x star, they've got to be equal to 0, right? So the first constraint, the blue constraint, lambda 1 doesn't come into it. Lambda 1 is equal to 0, and so the KK, you know, the sort of the Lagrange multiplier equation here looks like that. So at this x star, what does f of x looks like? Well, we've got the gradient of f is 2x1, 2x2, right? That looks like that. And then I've got lambda 2 times the gradient, the derivative of G2 with respect to G1. Well, that's just going to give me a take away lambda 2, right? So the derivative of G2 with respect to G1, sorry, with respect to X1 is just -1. So I'm going to get a lambda 2 there. That's going to be equal to 0. And then differentiating G2 with respect to X2 is going to give me X2 over 2. And then I've got to multiply that by lambda 2. So here I'm going to get lambda 2 x2 divided by 2 is equal to 0. So that's the KKT equations. I've also got the G2 is equal to 0. So I've got to also have x1, negative x1 plus x2 squared over 4 plus 4 is equal to 0 because I'm on the boundary there. Okay, so now you can solve this if you want. The solution is, you can see what the solution is just from the diagram. That's x star is equal to 4, 0. Right? So knowing that, let's plug that into these expressions here. So once I know the solution to this, then I can figure out what lambda 2 has to be. I just have to look at this first equation here, right? So if the true x1 is equal to 4, then lambda 2 is going to be equal to 8, right? And the last bit of the KKT expressions, KKT conditions that I have to check is that all of my lambdas are greater than or equal to 0, and they are, right? So you can go ahead and check if x1 equals 4, x2 equals 0, and lambda 2 equals 8, that everything here, all of these equations are satisfied, and they are. So this actually works out. So that's sort of doing things in reverse, right? Like I've assumed I know what the solution is here, and then I've just plugged in to make sure that everything checked out. If you wanted to solve this not knowing what the solution is, then you would need to solve these 3 equations here simultaneously. And you can see that that's messy because they're nonlinear equations, but it's be possible to do, and we have a framework for doing that here. Importantly, I've got the right number of I've got a small number of equations to solve here. I've only really got 3 equations because I could jump to not having lambda 1. Yes, once I know that lambda 1 is not activated, then I've only got this equation to solve here for my Lagrange multiplier. Okay, one more. You notice that this is a non-convex set. So the final example is a non-convex set because we've got these little chunks in it here, right? So I can find points within this set where if you connect them by a line, they go outside of the set. So this is a strange one. But it turns out that the KKT conditions actually work out here, and we can, you can sort of see what's going on here. So let's just explore that a little bit. So the minimizers here, so the minimizers are going to be, let's draw them in little crosses, they're going to be at the corners, the 2 points of this set, right? And so that's because it's the same, the overall true minimizers at the origin, and you can see that those points are sort of the closest that we can get to the global minimizer. So, my minimizer is going to be at approximately, what is that? That's x equals 3 and then approximately plus minus 1. And what does that mean? So, either my active set is either, if I'm up the top, then the blue constraint and the brown constraint are activated at once. So up the top, that point there is at the intersection of the blue and the brown curves. And so that means that I've got 1 and 3, oops, 1 and 3 are the active constraints, or I've got I of x star equals 2, 3. Right, so I'm at the bottom possibility here. I've got the red and the brown constraints activated at once. So let's look at one of those. So assuming that I'm at the top minimizer here, where the constraints 1 and 3 are activated, well, what do I have there? What would the KKT conditions look like? So they'll look like f, gradient of f evaluated at that point, plus lambda 1 gradient G1 plus lambda 3 gradient of G3 are equal to 0. Right? So that's what my KKT condition, what the main condition looks like. So the lambda 2 doesn't appear because of this top candidate minimizer here. The red curve is not activated. The red constraint is not activated. So I've just got the first and the third. So we've got an expression that involves x1 and x2 and lambda 1 and lambda 3 here. Let's assume that we know that x equals 3, 1, right? And so if you differentiate, if you find these gradients and you differentiate with respect to x1 and x2 and plug everything in, this leads to a couple of equations. So firstly, 6 minus lambda 1 minus lambda 3. So that's when I differentiate all of this stuff here with respect to x1. If I differentiate with respect to x2, I get 2 lambda 3 is equal to 0. And I've plugged in x1 equals 3, x2 equals 1 there. So I'm evaluating this at the minimizer. So there's a system of 2 linear equations. We can solve that for lambda 1 and lambda 3. So that gives me, if I solve that, I'll get lambda 1 is equal to 2. That's greater than 0, tick, right? That's what I need for my KKT conditions. And I'll also get, well, lambda 2 is equal to 0 and lambda 3 is equal to 4, which is positive as well. So again, tick, tick, the KKT conditions actually check out here, even though we have a non-convex set. So hopefully that demonstrates that this is a really powerful idea that is very, very useful and gives us actually a framework for solving these constrained optimization problems with multiple inequality constraints. So it's like a generalization of my Lagrange multipliers method, and you can see that it's sort of in those examples that everything sort of hangs together and it all works out. So what's left for us now is to go and prove the KKT conditions prove that theorem. It's a long-winded theorem, so it deserves its own video, and that's what we'll talk about next time.